Yes, here we are once again at the physics video lecture. This is Physics 105A video lecture 14. So let's begin with some review this time. We've already made it up into the complex numbers. We did a whole section on that. But I want to return to a couple of homework problems and just go through them and see how far it takes us. We're both actually 3 problems all told. Excellent homework problems. And we'll start with, so let's just call this homework review. Now that we've seen this stuff a couple times, we had the potential energy function for gravity. So I'm going to be as thorough as I want to be. So we had F equals minus mg. This was under the scenario that x is the positive direction, and that's the weight of an object. And then we had the potential energy minus the integral dx prime, some a to x here. So we had minus times minus is plus, so we had mgx plus some constant. So that was the potential energy gravity here on the surface of Earth. And if we were to graph that, so mgx plus constant versus x, it's just a straight line. Okay. And we now know the derivative of this potential energy, or negative derivative, is the force. Okay. So negative derivative of this gives us that force. Good. So that's gravity here on the surface of Earth, and that's free fall if I launch things straight up and down. The other gravity, so this is the one kind of gravity. The other one, though, was we're just going to call Newton gravity. And it's the same gravity after all. It's the same Earth, but it has a completely different form. F is equal to minus g m over r squared, the famous inverse square law. And u of x, if you integrate that up, actually let's say u of r. And we're going to spend a lot of time with gravity, actually this semester and next semester. But you guys have seen this before, I'm sure. So u of r is minus g m over r. First power, right? Force is the second power, this is the first power. And what we want to do is compare these because they look so different. But what I'll do is I'll stack the 2 graphs. Well, since we have that one right there, the Newton gravity graph, you actually have to leave space under the axis because it basically looks like that. Okay, so this was u of r. That up there was u of x. Same Earth though. So what is the relation between these 2 potential energy functions? This one here and this one here, represented by those 2 graphs. Now we have to know a couple of things. So in terms of this Newton gravity, okay, for F equals minus g m over r squared, what we make use of and what we're going to prove rigorously next semester is that a uniform or just a spherical mass distribution of radius r acts as though all of the mass were concentrated at the center. Okay. So for this sphere, which is now of course going to represent our Earth, and we can imagine we're standing up here, okay. Didn't quite work. Anyway, at the surface of Earth, at R equals capital R, F is equal to minus GM over R squared. Okay. GM over capital R squared times M. And this expression here is our lowercase g, okay, minus g times m. Okay. So that's really important. Make sure you recognize gravitational constant, mass of Earth, radius of Earth squared, that is g. And if you've never done this, you should actually look those numbers up because they're wild. Okay, 10 to the minus 11, 10 to the this, 10 to the that. Combine the numbers in this form and you're actually going to get the 9.8 meters per second squared that you're so well aware of. Okay. So what we want to do is now reconcile, like I said, these two formulas here. And we're going to make use of this fact, so I'll just put it here one more time. G is equal to GM over R squared. Go ahead and, like I said, plug the numbers in, figure that out. Recognize it. Okay, I can actually use these two pictures here because let's call this capital R right there. And I'll even use a different color. Then there is the value of the potential energy at capital R. You just plug it in. It's a constant. And if you want to approximate this curve by a straight line, you can take a Taylor series of it. Okay. So that's what we're going to do, because what we're going to find is the approximation of this potential energy by a straight line is going to give us a straight line identical to this one. Plus, if we take another term, it's going to give let's say, correction. So we're going to get a correction to the mgx, because this law here is more exact. Okay? This is just local near the surface of Earth. This one goes all the way out to the far reaches of space. So that's what our goal of doing the Taylor expansion was and is to match up these two lines, the red one and the blue one up there. And if you're close enough to the surface of Earth, this curve is approximated by that straight line. Okay. Good. So we're going to do a Taylor expansion of U of R. So expand U of R in a Taylor series, and we're doing it about R is equal to capital R, just as I've drawn right here. So there's our function, and we're just going to go ahead and take those few derivatives. So let's go ahead and do it this way. U of R is equal to minus GMM over R. U prime of R is equal to minus GMM. And then we have R to the minus 1 power, so we have minus 1 over R squared. And those two are going to cancel, so it'll be plus again. And U second derivative of R is equal to GMM. Now we have R squared in the denominator, so it's minus 2 over r cubed. So we've collected our 0th, first, and second derivatives. And the Taylor expansion, of course, is u of r equals u of capital R plus u prime evaluated at capital R, r minus r, plus 1/2 u double prime evaluated at capital R, r minus capital R squared. And we could, of course, do more if we wanted. In fact, this function is easy to do as many as you want, but we're going to stop it here at 2. And let's go ahead and evaluate it. I think everything will be on the board that we need. Yeah, by the way, make sure you recognize what I'm doing here. We did a section on Taylor expansions, doesn't matter what letters you use. These are, of course, constants. About the evaluation of a function at a particular point gives a constant, and the variables are here in the parentheses. So we find u of r is equal to, and we'll go ahead and plug everything in. So we'll have minus GMM divided by capital R. That is just a constant, okay? Now the u prime is going to get interesting. Positive GMM over R squared. GMM over R squared, positive, because I plugged that in there, and now R minus capital R. We're going to do this one more. We have 1/2 u double prime of R. You see those 2's are going to cancel. We are going to get the minus sign. So we're going to keep the minus sign. GMM over R cubed. Okay, so I've evaluated the derivative. 2's canceled, got the minus sign. R minus capital R squared. So what are we going to make of this? First of all, I can draw everything here. Notice that we have G capital M over R squared, which is just equal to G, lowercase. I'll do this in 2 steps. This one, we don't care about it, it's just a constant, okay? This one here is plus, okay, there's the G, right? So this one is G M R minus capital R. Now this one's interesting. We have GM over R squared, but we have another power of R there. So we have minus G M R minus capital R divided by capital R. Now let's leave this one out here for a moment. So we'll just keep that R right there and R minus capital R squared. Okay. So this is U of R, and if you neglect this expression here, you just have the point slope formula. Now what I'm going to do is let x be equal to R minus capital R, because this was the distance from the center of the Earth, and this is the surface of the Earth. So the difference of those is the distance above the surface of the Earth. Okay. And now what do we have? We just rename this thing u of x. Okay, we're not going to give it a new name. We've got a constant. We've got mgx. I just switched the order there because it's familiar. Minus mg x squared divided by r. So again, these two terms here, and in particular this straight line one, that is just our point slope formula for the straight line. Okay. So we've actually already achieved our goal, but I told you guys to do an extra derivative here because this one is also going to be interesting. So let's just underline this as the approximation when this x is sufficiently small. But we can do this, we can do one more interesting step for u of x equals, we've got the constant, we can factor out the mgx that's common to both of these, and then we have 1 minus, and what's left over is an x over r. Okay. This expression tells us something new. It tells us the validity of this original formula. Remember, mgx is just what we talked about here on the surface of Earth. If we go to Newtonian gravity, we've got c plus mgx. Now, as long as x is much less than the radius of Earth, okay, as long as x is much less than capital R, we can just neglect this altogether. Okay. So the linear approximation, which is what this is, holds when x is much less than r. Okay. So we can neglect if x, the distance above the surface of Earth, is much less than the radius of Earth itself. If x, over r is not much less than 1, then you're going to have to deal with it. But of course, for anything near the surface of Earth, even up to a couple hundred miles, this is still, or a couple hundred kilometers, this is still a very small quantity. It doesn't play much of a role. So anyway, that's the meaning of this whole assignment with the Taylor expansion. I don't think I left anything out now, so leave some room, fill in any words of wisdom that you need for understanding this. And yeah, this was our original potential energy function near the surface of Earth. Good, so you really get to see where the Taylor expansion is. And by the way, this term here, minus mgx squared over r, that's really filling in this difference. It's the difference between the straight line and the actual curve for a certain distance. Now, if you went far enough, you'd need more terms in your Taylor expansion, and at that point, you'd probably do something different. Okay, so that was the first discussion that I wanted to have here. Yeah, this one you want to add to your repertoire. Very, very useful problem. See what the Taylor series is good for, and you just want to become comfortable with doing a few steps there and realizing what you're doing. Okay, let's see what's next. Let's send this up here. Okay, since we are talking about oscillations these days, and we're about to move deeper into that, I'm going to go back to the back to that formulation with the conservation of energy. And I'll go ahead and repeat the derivation. We get half m dx dt squared plus u of x is equal to e, and then we separate variables. We get t is equal to plus minus integral dx prime 2 over m, e minus u of x, e minus u of x prime square root, and then, from some constant to x, and here also, and I'll even put this note, if u of x is equal to 1/2 kx squared, and that was a homework problem that I had set up with you guys, then x of t, you can integrate the thing, get your inverse cosine, invert it, is a cos omega t plus alpha, where omega is root k over m. So that's a complete treatment of that thing. And e is 1/2 k a squared. That's a constant. So that's, of course, one very important application. So this was the harmonic oscillations. The more general oscillations, you can't necessarily even do this integral, but it's interesting nonetheless. So for u of x is equal to b times magnitude of x to the nth power, we went ahead into there as well, right? And then we had e was b a to the nth power, and we went into that integral and got the period of oscillations is t was equal to 4 of these things from 0 to 1, 0 to a, and I'll draw that graph in a moment. Dx root 2 over m. We had b a to the n minus b x to the n. Okay. So we had that. This, of course, was a special case where n is equal to 2, and we did a couple other ones. What we were interested in was the limit n goes to infinity. And this is a tricky one. What I had shown you, though, was that we can pull all of the physics out here. So we pulled the physics out, so I'll put question mark there. Oh, and by the way, let's go ahead and do our graph. So we've got minus a, and then, and we're thinking mostly of the larger n. N equals 2 is just parabola. As n gets larger, this gets flatter and flatter. And our energy, is the value at A. Okay. So let's repeat this calculation. So we're going to pull out, we got this root 2 over m. Apparently we also have a square root of b out there. And we've got this a to the n minus x to the n left over. What I do is I let y equal x over a, dy is equal to dx over a. So I've got the dx is an a dy, and then my a to the n minus x to the n turns in a to the n minus a to the n y to the n. Okay, so I can pull out a to the n over 2, and I'm left with this 1 minus y to the n 0 to 1. Yeah, so when the dust settles, we have 4 root 2b over m, and we have a to the 1 minus n over 2. Now you can look up the gamma function, the beta function, or the beta function and get expressions for this. But I'm interested in the limit as n goes to infinity. And it turns out that this integral, as n goes to infinity, this red line here just becomes arbitrarily flat and then arbitrarily steep. And you can show, it's a little bit of a tricky limit proof, but you can show that this is equal to 1 for n goes to infinity. And yeah, then we were going to say, okay, that was a square well potential, vertical walls. So now here's the last step that I want to make sure you see. We've got this a to the minus n over 2, and we can express e in terms of that. Okay. So for the problem we're going to do, we just keep a to the 1 power. We've got a to the n over 2 in the denominator. So use a to the n over 2, which is, like I said, it's in the denominator there, equals to e divided by b. Okay, to the 1/2 power. So when you make that substitution, be careful what's the numerator, what's the denominator, and you let that go to 1, right? When you pull that out, you made no approximation at all. When you take the limit n goes to infinity, this 1 is also not an approximation. That's an exact result. And what we find is, so yeah, go ahead and make sure you can do that. All these steps are important. What we then find is that we're going to put that v naught period is equal to 4a, because it's just bouncing back and forth. It's just bouncing back and forth with constant speed. It just has a turning point, instantaneous turning point, but otherwise it's constant speed. And e half m v naught squared. So what you do is you express this thing, put everything in there, then this substitution with the e half m v naught squared, because it's pure kinetic, will give you this expression, and then it's a nice consistency check. So yeah, that was one I just thought I'd repeat with you. Make sure you can do all these steps clearly. It's a good one. And I'll stress once again, pulling all of these things out in front of the integral is pulling all of the physics out. This was all important physics, and this was just a number. Main thing we want to know about this number is that it's less than infinity, okay? It's an actual number. And so good, that's that problem that I wanted to talk about. I mentioned a third one. Not sure what one I was thinking of. Okay. Okay, let's see what we want to do next. So many possibilities. Yeah, I had one more result before we get back to the complex numbers. So now we're going to talk a bit about this right here. Okay, we're doing the harmonic oscillations. So our third problem here, or actually this is going to be a slightly new topic, but we're working with the harmonic oscillations. Yeah. And the key, what was important out of this analysis was that when n equals 2, remember the parabola 1/2 kx squared, when n equals 2, right here, right, when n equals 2, 1 minus 1 is 0, you have a to the 0th power just constant, and we in fact have the amplitude independent frequency in period. Okay. Harmonic oscillations, so u is equal to 1/2 kx squared. And I'm just going to write down everything we have here. X equals a cos omega t plus alpha. Omega equals root k over m, and of course t is equal to 2 pi root m divided by k. All right. And both of these, which are of course equivalent to each other, show that period and amplitude, or period and frequency are independent of amplitude. That's one of the defining characteristics. Okay. So here, words, period and frequency independent of amplitude. Good. So there's another important property. So this is such an important property, gets a star here. That's kind of a defining characteristic. So there's another type of defining characteristic that we want to talk about. And for that we have to define the time average of a function. So the time average, and what that is of a function f of t, what that is 1 over t f of t dt, 0 to capital T. We could, give it a square bracket or a line over the top or something we could call it time average. And it's clear that the time average of the position for harmonic oscillation is 0. Okay. Time average is 0. And I'm going to have you show all of these things. I'm just going to mention it. And for oscillations, we can identify this. This was just any old time, but we can actually identify it with the period. So 1 over the period times integral 0 to the period, that time, or some multiple of the period, because it's going to be the same. Okay. So for oscillations, let's see, for harmonic oscillations, x of t time average. Actually, we don't have to have the integral there, but I wrote the argument there, but we can write it in there. X of t time average is equal to 0. V of t time average is equal to 0. Well, if you integrate the cosine, you're going to get the sine, and the sine over a complete period, is going to vanish, right? The final point is going to be the same. And the same thing here, if you differentiate, you're going to get the sine time average integrated over a complete period is also going to vanish. The next one is more characteristic, although this is important, very important. Time average vanishes. The time average of the kinetic energy is equal to the time average of the potential energy is equal to 1/2 of the total energy. So this is that important property of harmonic oscillations. It's not true for other potentials, it's true for the x squared potential, okay? And let's call this a homework problem. Homework. In fact, these of course are trivial, but you may as well do them also, and then do this one here. And I'll set this one up. So the time average of the kinetic energy is equal to 1 over the period, integral 0 period, and we have 1/2 mv squared, right? X dot squared, but the x dot here is going to just bring out an omega. You get a minus sign, but doesn't matter, that's going to square away. So we're going to bring out omega squared a squared, because it's 1/2, x dot, just so we have it, minus omega a sine omega t plus alpha, right? Omega squared a squared sine squared, omega t plus alpha dt. And you're going to have, you find out what you get. And you'll do the same thing for the potential energy. There you'll have 1/2 k x squared, right? Potential energy 1/2 k x squared. So 1/2 k a squared cosine squared. But it's going to be pretty easy. This, so you'll have a cosine squared instead of a sine squared over a complete period. It shouldn't be hard to show that those are equal. And you'll also notice that k, so m omega squared is equal to k. But yeah, this is an important one, namely that the kinetic and potential have the same time average. So that's also a crucial, important feature along the lines of this one as well. It's 2 stars. Okay. Now, well, we're almost up with our time. I'll just put up on the board what we're going to do next. So yeah, these are basic. Now the review you don't have, the review you want to write up and have in your notes, right? Have a good look at it, really understand it. This here you want to turn in. Okay. This here you want to turn in. Okay. So here I'll just put up where we're headed next time, because this is a good place to break. Say all these discussions are very physical discussions of oscillations, and the harmonic oscillations are just one kind of oscillation, but now we're zeroing in on those, and so we're going to use the whole complex number formalism because it's so great. Okay, so I'm just going to write next oscillations and complex numbers. You know, the last thing we had done the other day was to find that if z equals e to the I omega t, then z second derivative equals minus omega squared times z. Okay. That's really crucial because that is the differential equation of the harmonic oscillator, now with complex numbers, and these are just so convenient to work with. There's a whole world of interesting stuff with complex exponentials and complex functions in general. So what we're going to do is work with the complex exponentials. If you say, yeah, where's the physics? Well, we can always take the real part, and then that'll peel the cosine right out of here, okay? But we'll do that next time, and we'll see you then.